Hi, I'm going to show you how to implement and visualize the recursive solution for this problem. It seems like a lot, but we're going to step through it one step at a time, and I promise you at the end, you will easily be able to implement the solution yourself. Let's talk about the problem. Balanced binary tree. A height balanced binary tree is a binary tree in which the depth of the two subtrees of every node never differs by more than one. Let's look here. In this example, the height of the left subtree is 1 and the height of the right is 2. The difference between those is 1, so we're good. We can return true. It is balanced. In this example, left has a height of 3, 1, 2, 3, and right only has a height of 1. The difference between those two is 2, which is not good. We have to return false. This is the algorithm we use. We call this function DFS recursively, and we use this little trickery here in JavaScript, math.abs, which takes the difference between left and right and always returns a positive number or integer. If it's greater than 1, we set res to false. We initialized it as true, and at the end, res is what gets returned. Let's look at the first example here. Left is 1, the height of the tree is 1. Right is 2, the height is 2. So we take the difference between those, which is 1. Is 1 greater than 1? No. So we don't set res to false. We just return what it was initialized as, which is true, and we're good. Recursion starts from the root. In this example, root is 3, so we call DFS on 3. And first, we're going to go all the way down the left because in our algorithm, node.left is above right. So if it was the opposite, we would check right first. But since we're checking left first, we go here, step 2, we call DFS on 9. And then we have to check left first again. So we go down here. It is null, so we return 0 up. Then we have to check our right node and it is also null, so we return 0 again. And now we can do the arithmetic on DFS 9. In this case, 0, there's no difference between the two, and it's not greater than 1, so we don't change res. And math.max plus 1 of left and right equates to 1. So we return 1 up to our root. Left is equal to 1. Great. Now we need to get right. So we go down here and call DFS on 20, which then again, we're going to check the left side all the way down first. All right, so that means we call DFS on 15. Then we check DFS on null, what's to the left of 15, null. That returns 0 up. And then we call DFS on right, what's to the right, null as well. Move this up and we can do the arithmetic for DFS of 15. Again, it's not greater than 1, so we don't change res, and we return only 1. So 1 gets returned up here to left. Great. And now we need to get right. So we call DFS on 7. What's to the left of 7? Null. That returns 0. What's to the right of 7? Null. That returns 0 as well. Get rid of this. So now we can do the arithmetic again. It's not larger than 1, so we don't change res. And this entire node returns 1 back up here. And we can do the arithmetic for DFS of 20, which is going to give us 1 minus 1, 0. It's not greater than 1, so we don't change res. And math.max between 1 and 1. The largest number here is 1, so we do 1 plus 1. And that returns up to our root node. Right equals 2, and we can do our final calculation. So 1 minus 2, the difference between these two numbers is 1. It's not greater than 1, so we do not change res. And that means we just return true. That's it.